Welcome to lecture 2, which will deal today on organometallic compounds. It will be the first of 3 lectures approximately where we will be covering stoichiometric organometal compounds, and with stoichiometric it is meant that the reagents we will encounter are used in a stoichiometric rather in a catalytic fashion. The compounds we will deal with today are 2 classes. I'm sure you know quite a bit. These are organolithium compounds and Grignard compounds. In the script you will find some literature I would recommend you might want to look up, or I might also be able to post it on the web, which has an excellent chapter on all 3 of these organometallic chapters we want to cover. And so you can look it up also in the library, or as I say, I might be able to post it online. Let's very briefly introduce the concept of organometallic chemistry. We have on the one hand organic chemistry, and here we usually deal with covalent bonds of various types. They are more or less rigid in geometry. And at least for the bonds itself, we have a clear idea how geometry might look, how an overall conformation might look, might be of course different. And unless we deal with oxidation and reductions, most of the time we encounter fixed oxidation states in these organic compounds when we do transformations. And then on the other hand, we have inorganic chemistry, and here we deal mainly with ionic bonds where a metal is involved. Geometries can differ quite a bit. And can also vary from metal to metal. Sometimes we have square planar, sometimes octahedral, sometimes tetrahedral geometries. And also we have, in general, multiple oxidation states. And somewhere in between these 2 fields, we have organometallic chemistry, which obviously is very, very important for organic synthesis because it allows you to do a number of organic transformations otherwise not possible. And the definition of organometallic chemistry, the pure definition, sometimes it's used a little bit more lax, that we have the feeling that any type of organic compound which somehow has a metal attached to it or is involved to is an organometallic compound. That is, of course, not true. The definition for organometallic compounds is that these should be compounds which contain a metal carbon bond so for example, take the anion of acetylene, which might have a counter ion like lithium, and we all know that this is probably a very quite covalent arrangement here where we have a lithium carbon bond here, so this would be considered as an organometallic compound. And opposed to this, if we, for example, would look at lithium methoxide, the commonly encountered base, and of course also something we think of as an organic compound, of course, although it's an ionic salt here, but this would have a lithium oxygen bond and therefore would not be, in the definition, be an organometallic compound here. Organometallic compounds have been around a lot, also in our daily life. I'm sure you're not so young any longer that you have forgotten that not too long ago we would have compounds in our gasoline which would qualify as an organometallic compound. Tetraethyl lead was used as an anti-knocking agent in gasoline. As you all know now, with the introduction of the catalytic converters, one had to find alternatives because lead is poisoning the catalysts, the platinum and palladium catalysts being found in these car converters. However, on the other hand, also lead is a very toxic compound, so it was also good for the environment and for the living beings to replace this compound. As I already pointed out, the general formula for the organometallic compounds, I will use the letter R as a generic abbreviation for residue, M for metal. And the key feature of these organometallic compounds is their polarity, in that the carbon bears a partial negative charge, and the metal, of course, is the positive center here. And this, of course, is distinctly different to the normal CX bonds we encounter, where we have, think about, for example, an alcohol or an alkyl halide, where we have more a positive charged carbon here and a negatively charged heteroatom. And so by going from an alkyl halide, for example, to the corresponding alkyl methyl compound, and we will see in a moment how we do this, and I'm sure you know this already. Basically what you do is you reverse the polarity of that carbon from being positive to a negative one. There's a word for this for which the English could not find an impression. There's a German word for that. And this is the word Umpolung, and that word is also in the English language now. So the organometallic compounds are having the key feature that they have a negative, that they are source for anionic carbon, and therefore that they can act as nucleophiles. And we know, of course, some carbon nucleophiles already, without that we really have to go to organometallic compounds. So one example, of course, is the cyanide anion, which, if you consider that the metal atom might coordinate to the carbon, you might consider as a organometallic compound. However, it's also known that it's really more an ionic compound where the metal is not really located, so might be also considered an anionic compound. For example, potassium cyanide. And this is, of course, a great source for a carbon-1 nucleophile, which will readily undergo nucleophilic substitutions. This way allowing to carry out a C1 homologation, which, for example, is very useful if you hydrolyze, for example, the nitriles. You might arrive at carboxylic acids this way. Other carbon nucleophiles, you of course also know, are aromatic compounds. And there are two reactions where you use these aromatic compounds as a carbon nucleophile directly in order to form a carbon-carbon bond. And this is either the Friedel-Crafts alkylation reaction requiring a Lewis acid catalyst, such as aluminum trichloride, for example, and then also the corresponding Friedel-Crafts acylation. Which allows you to form carbon-carbon bonds. But fortunately, this is not all what we have. The organometallic compounds allow us a much greater variety to make carbon nucleophiles, and this is what we should look at today. Okay, before we actually learn a little bit how to make these and how to use these, let's make some more general considerations here. And so let's first look at the carbanion part. You can, of course, envision various types of carbon substituents being attached to the metal. And depending how acidic or basic the substituent is, the more stable and the less reactive the organometallic compounds are. If you look at some very typical scenarios here, we might have a carbanion being attached to an sp, or to an sp2 carbon, or to an sp3 carbon. And the common feature is that the stability of such carbanions becomes greater the higher the S character of that carbon is, because more S character of a carbon means that the orbitals are closer to the nucleus, and therefore the negative charge is, you can think about this, bound more tightly, and therefore these compounds become more stable. So we're having here an increase of stability, but then in return, this means that in the other direction, we see an increase in reactivity. And to be more specific, the two types of reactivity such carbanions can exhibit is either nucleophilicity or basicity. And we will see these two types of reactions over and over in the following examples. If we look here for a moment at the carbanions being on an sp3 carbon, then we can make some further reactivity order here, and that is the more alkyl groups we put on that carbon atom. We learned last time that alkyl groups stabilize positive charges by hyperconjugation, and by the same argument, alkyl groups destabilize carbanionic centers by their donating character. And therefore, if you go from a primary carbanion to a secondary carbanion to a tertiary carbanion, again, they are less stable, but highly reactive. And the second consideration we can do here is the metal, to look at the metal part. And of course, also probably not surprisingly, the higher the electron differences between the carbanion and the metal are, the more ionic, the more naked the carbanion is, and usually the more reactive it is. And therefore, if we, for example, consider a lithium anion, the corresponding Grignard compound or a copper compound, then what we see here again in this direction, the electron differences become smaller and smaller. The compounds become more covalent. The anionic character is not as strongly expressed here. So again, in this way, we see an increase of stability. And in return, in this direction, we again see the increase in reactivity. Now, with the later statement, we have to be a little bit cautious here. In general, this is absolutely true. The organolithium compounds are much more reactive than the cuprates. But the caution which you have to do here is that nevertheless, you have to look at the substrate these organolithium or organocuprates reactions react. And let me just recall the HSAB principle. The principle of hard and soft acid bases. And that was a concept where you would argue that a hard compound, a more ionic compound, would react preferentially also with a hard compound, and a soft compound, a more covalent bond, would also react with a more soft counterpart. And so although these lithium compounds are generally more reactive than the cuprate compounds, they are nevertheless, because of these type of principles here, they are nevertheless substrates. The cuprate will react, and the organolithium compound will not react, because the hard softness is not correct here. So again, in general, the statement is right, but keep that hard and soft principle in mind. So let's now start talking about how we actually can make these type of compounds. And there are for the organolithium and organomagnesium compounds, there are three methods available. And the first method, I'm sure you all know, is the reductive replacement of a halogen done by a metal. And so the classic examples are that you take an alkyl halide, and you can either treat it with magnesium metal or with lithium metal, and therefore thereby forming the corresponding organolithium or the organomagnesium compound. Now to have the stoichiometry right here, you need 2 lithiums here, and you are forming lithium bromide as the additional product. How does this work from the reaction mechanism? It is believed that the metal initially is carrying out an electron transfer to the alkyl halide. So you're forming something like a radical anion. And the metal plus cation. And then in a second electron transfer step, which can be either the same metal, in the case of magnesium, where it goes from magnesium 1 to magnesium 2, or it can be the second lithium atom here, you are transferring another electron, thereby breaking this bond, forming bromide and the organometal compound. Now that's an interesting reaction mechanism which will also help you to do sometimes the synthesis. Because very often, although these reactions are in general very, very fast and facile, you might have encountered the problems that nevertheless a Grignard or an organolithium compound might not start working because it's for some reason kinetically disfavored. There might be, the lithium might not be pure enough, the surface might be not exposed enough, and so sometimes the reactions do not go very fast. There are a number of tricks one can do in order to make such reactions go more smoothly. In the lithium case, it was recognized that very often if you add catalytic amounts of a biphenyl compound, and the biphenyl compound which has been used here is the bis-terz-butyl biphenyl compound here, that this might rapidly enhance these type of reactions. Because what is happening here is that the lithium preferentially very easily transfers an electron to this aromatic system, thus making here the radical anion. And then the radical anion is transferring its excess electron to the alkyl halides. And again, that, as I say, might sometimes greatly accelerate your compounds. With the Grignard compounds, there are also all kinds of tricks. It's known that magnesium bromide is accelerating sometimes these Grignard formations, so you might form, one is able to add this. Very often you need to clean the surface of the magnesium, so adding dibromomethane very often is doing this. This Grignard rapidly starts, dibromoethane. This Grignard rapidly starts, eliminates magnesium bromide and makes ethylene, which dissolves. This way you're forming magnesium bromide. And overall this, if you add some small amounts of this, you clean the surface of your magnesium, and at the same time you also form the catalytic salt, which also sometimes helps you. Nevertheless, very often even this might be difficult, especially if you try to prepare a Grignard reagent from an alkyl chloride rather than from a bromide. And another trick you can use is the so-called Magnesium, where you start from the magnesium salt, magnesium chloride, and you treat it with a stoichiometric amount of lithium in THF. In the presence of naphthalene, which has a similar effect here like the T-butyl diphenyl. And this way, what is happening is that you are forming magnesium plus lithium chloride. Now you might say, well, that's the same thing. Why not starting with the magnesium immediately? But if you use this reductive variant, you form very, very highly dispersed, very small particles of magnesium. If you do this reaction, you can see that it is finished if you suddenly have something very black precipitation in your flask, because it's so highly dispersed that has not this metallic shine any longer, but it is pitch black. If you take this on air, it might start fire. That shows you suddenly how reactive it is. Usually magnesium turnings you can simply handle on air without any problems. And so this type of highly reactive magnesium is very often a good idea if you want to make a difficult grignard, for example, from an alkyl chloride rather than from an alkyl bromide. If you do these type of grignard reagents, we already said that it has a negative charge here on that carbon, which can act as a nucleophile. And we all know that normally alkyl halides are very good electrophiles. So the first question now is there the danger that the nucleophile which is created here might actually react with the still present starting alkyl halide, forming a SN2 reaction and simply making a nucleophilic substitution here. Now, in general, if you have these alkyl halides, this is not so much of a problem, because this reagent is relatively hard. This is much softer. And as we will see, and as you probably all know, is that such grignard reagents react very easily with carbonyl compounds, but they do let the alkyl halides alone. Now, that is not true for all of the alkyl halides you can use. You see coupling products which is, of course, preparatively sometimes very useful, and it's the so-called Wurtz coupling. When you use allylic halides and in the same range are the benzoylic halides and also propylylic halides. They tend to undergo, for example, if you prepare the lithium compounds, they tend to undergo, after formation of this, a SN2 reaction with the starting material. Which then will give you the overall coupling product. And therefore, there's another variant you can use here in order to not run into this type of problem. And this is the so-called Bria type reaction, which is especially suitable if you want to prepare organometals from allylic, benzoylic, or propylylic compounds, is that you can have the electrophile you would like to react it with already present in your reaction flask. So for example, take allyl bromide, take cyclopentanone, and then add magnesium, polar solvents like ethyl ether, most commonly used And then you form the grignard in situ, and because the carbonyl compound has a much higher reactivity for the grignard than the alkyl halide, you form immediately the addition compound, and you're not running into the problem of the coupling reaction. Okay, you will see we have to do some heavy editing on this board movement here. Okay, so let's take this one. Where did I put? Oh, okay, here it is. The second method I would like to introduce for preparing organolithium and organomagnesium compounds is the metal halogen exchange. Which will take place as follows. You can also start again with your halide compound, but then at the same time you can have a already formed alkyl lithium compound which then might exchange the lithium and the halide atom with each other. Now this reaction can only be productive if you go from a less stable more basic organolithium compound to a more stable less basic compound here. Otherwise, it will obviously not work. If the basicities are too close, you will get mixtures. Or if this organolithium would be more basic than the other one, the reaction would not proceed at all. So then the typical examples are, for this type of approach, that you will start with a alkyl lithium compound. So having here sp3 center, we talked already shortly on acidity. Alkanes, of course, have a very low acidity. So these compounds are highly basic. And then in the end, you will go to a, in this case, organolithium compound, which will have here an sp2 or an sp hybridized carbon. So this is usually productive. And therefore, in general, will work quite nicely. Now, with certain alkyl lithium compounds you form, the resulting alkyl bromide here might be a problem. Let me give you an example for this. So if you start with butyl lithium and take an alkenyl halide, then your reactivity should be okay. And indeed, the metal halogen exchange is rapid. And you are forming the corresponding alkenyl lithium compound. But again, at the same time, you are forming butyl bromide. And these vinyl lithium compounds have the tendency to be very decent nucleophiles for alkyl halides. So what will happen here is, again, it might be preparatively useful if you are interested in the butyl compound. But what will happen here is that you are forming, again, the Wurtz type coupled product by simply reacting the vinyl lithium you create here with your alkyl halides. This complication can be overcome, though. And again, there's a nice trick to do this. That you start with your vinyl halide, and now as the base you're using not the N-butyl lithium, you're using the tert-butyl lithium. It's highly reactive. Now we go from an N-butyl, N-alkyl substituent to a tertiary substituent. These are even more reactive. But this is not the point, because both of these initial metal halogen, lithium halogen exchanges work quite nicely. The point here is that you're using a second equivalent of T-butyl lithium. And the reason you do this is that you get the initial lithium halogen exchange. But now the tert-butyl bromide you're forming here will readily react with the second equivalent of the tert-butyl lithium and do an elimination here, generating isobutene. So T-butyl lithium now here with this alkyl halides, because it's sterically very hindered, it will not readily do the lithium halide exchange. Rather, it will do an elimination here. And this way, you're creating isobutene, which is a gas, and goes out of your reaction flask, and lithium bromide. So this is a way to overcome the complication you might encounter with the coupling products, again, which is specifically severe for alkynyl halides. It's not so severe for aryl halides. And these compounds, of course, are very useful. You can trap such alkynyl lithium compounds with electrophiles and introduce an electrophile here. And there can be many, many types of electrophiles which work for these reactions. So for example, you can take carbon dioxide, you form carboxylic acids. We will look at these type of reactions a little bit later. You can use dimethylformamide to make aldehydes, or of course you can use other carbonyl compounds like aldehydes or ketones. Many types of electrophiles will undergo now coupling reactions with the alkynyl lithium compounds. All these type of reactions have to be done at very low temperatures. Typically, what one sees in the literature is that the temperature can be anywhere between -60 and -120 degrees. Most commonly, you probably see -78, which is the dry ice acetone temperature you can create. But if you go to liquid air or liquid nitrogen, to be more specific, you can go lower in temperature. And then it also becomes a problem very often with the solvents, because at -100 degrees, most of the solvents are not liquid any longer. So usually -78 degrees, which is acetone dry ice. Here you are still okay with the solvents typically used like THF, dichloromethane. Of course, dichloromethane, not a good idea to do such type of reactions here. Diethyl ether. But if you want to go to -120 degrees, which then you usually generate by using pentane and liquid nitrogen, then you have to use solvent mixtures. And one famous one is the so-called trap mixture, which is a THF ether pentane mixture in the ratio of about 4:1:1. And there you can go really low in temperature without the danger that your solvent might solidify. Now also the magnesium halogen exchange for preparing Grignard compounds can be extremely useful. You might wonder, maybe magnesium turning to use is so convenient, why should I do it this way? But let me give you a good example. Try to make the Grignard compound of this para-iodobenzoic ester. Usually when you would do the Grignard reaction with magnesium, typical reaction temperature would be room temperature. Sometimes you might even have to heat it a little bit, 40 degrees or so. Now the Grignard reagent will form and then it would do what you expect a Grignard reagent to do. It will react with this carbonyl functionality here. And it will do that rapidly. And therefore, basically, you would form a polymer here if this is going on intramolecular, or you would simply get oligomers and coupling products here. And the reason for this is that Grignards react readily at room temperature with all types of carbonyl compounds. However, Grignard reagents do not react with carbonyl compounds at lower degrees, such as 0 degree or even minus 20. And so if you want to solve this problem, then what you would do is you would use an alkyl Grignard, and isopropyl magnesium bromide has been found to be very good for this purpose. Now you're again okay, you have an sp3 type Grignard, you want to go to an sp2 type Grignard. So in terms of basicity, this reaction should proceed, and indeed it does. And you can do this at temperatures like minus 20 degrees now. And at minus 20 degree, the forming Grignard now is stable. And subsequently, for example, treated with an aldehyde, you can trap it. And introduce the electrophile you might be interested in. I will have in the script a couple of more examples for these halogen exchanges. I would not like to show them all now. Maybe I give just one. Interesting aspect to take in, and this is that these metal halogen exchanges these are very, very fast. And this can be seen if you take a compound like parabromotoluene and treat it with N-butyllithium, then you could potentially get two types of reactions. You could get the metal halogen exchange, forming the aerolithium here. But the butyllithium being a strong base, it might also deprotonate an acidic proton. And we have already these protons potentially are more acidic than the alkyl, than the alkane, the corresponding alkane here. But these benzylic protons are extremely acidic because you would form a mesomeric stabilized anion. And nevertheless, what you're going to observe is indeed the metal-halogen exchange, simply because this is very fast. While the corresponding acid-base reaction is much, much slower, which might be intuitively against what you so far has encountered, because usually we think of acid-base type reactions, neutralizations, being extremely fast, but the metal-halogen exchange is a lot faster here. So this brings me to the third method you can use for organolithium preparations, and this is the metal hydrogen exchange. And this works for organolithium compounds very well. And again, what is the idea? The idea is you take a carbohydrogen bond, you treat it with an organolithium compound, and now analogously what we did with the halide in principle now can also occur with the alkane here. And again, the driving force must be that you have to go from a stronger acid to a weaker acid here. Or in other words, from the more basic organolithium compound to the less basic organolithium compound. And so the same principles basically we have just seen for the metal-halogen exchange also apply here. So let's look at a few examples. If I manage to get the right board here. So again, a typical approach where this should work is you go from an sp3 alkyl lithium, again butyl lithium is always used because it's commercially available. And then you might go to a compound which has hydrogens on sp2 carbons. And again, from the acidity point of view, you are okay here. This is the more basic alkyl lithium. Butane is the weaker acid. This is the stronger acid, so this reaction should work. However, as you surely appreciate here, you have 3 different hydrogens. Now note that this problem you don't have if you are able to place a halide when you do the metal-halogen exchange reaction. Then there's no issue of regroupselectivity. However, with if you do the deprotonation, very often you have equal types of hydrogens. And so the question is, which one is forming here? And indeed, very often they might all form. There are, however, substrates, very important substrates, where the deprotonation will occur selectively. And usually, if you have a heteroatom in your aromatic system, this will selectively deprotonate the ortho position for the reason that your N-butyl lithium compound might coordinate to the substituent and then selectively deprotonating the adjacent position. So this is a scenario which usually with aromatic compounds works very well. There can be other directing groups. For automethylation, nitrogen substituents are directing. Alkoxy substituents we already had. Protected alcohols. Or, for example, very good directing group are amide groups here. So a number of possibilities you have here in order to selectively address ortho positions. Usually, if you want to achieve a selective meta or para position, you should consider making the halide by the known methods we have, which are available, and do this way. Now, very briefly, let me say one word. I always have written so far these reagents as butyl lithium or alkyl lithiums. It is known that the real structure is not a monomeric structure like I always write it here for simplicity reasons. It's known that alkyl lithium compounds, and then also depending on the solvents, are forming oligomeric structures in solution and also in the solid state. There are X-ray structures of methyl lithium, butyl lithium in where it was crystallized from hexane, crystallized from THF. And it's known that they can make tetramers, hexamers, or even higher aggregates. Now, what this very often means is that because they are not so monomeric as we always like to draw it, it might affect the reactivity. And that is that the oligomers are much less reactive than the monomers are. And so very often you need to break up to go from the oligomers to the monomers. And there are a couple of reagents which will allow you to break up these compounds, these oligomers. And I will draw three very famous ones. This is tetramethyl-ethylene-diamine, commonly abbreviated as TMEDA. This will allow you to chelate the lithium here, and it does two things for you. First of all, it breaks up these oligomers because these are lithium alkyl clusters. And on the other hand, it also, since it chelates the lithium, it makes the carbanion more naked. So it becomes more reactive this way. Another now infamous compound is hexamethyl phosphor triamide. Commonly abbreviated as HMPA. Now this is an excellent reagent to break up these oligomeric structures, to chelate the lithium, to make very reactive alkyl anions. It's absolutely wonderful from a chemical point of view. However, the problem we have is also that this compound is highly, highly carcinogenic. It's one of the most toxic compounds which one can encounter in a laboratory, and not that something immediately happens to you, but it might have long-term effect. And this is why we avoid, or actually we are not using HMPA at all costs. There have been now a number of alternatives proposed which work just as well in most instances. And this cyclic urea derivative here, and you probably see a little bit the resemblance to the HMPA molecule here. This is called DMPU. This is a substitute for HMPA, having more or less the same good chelating properties, but it's a non-toxic compound. So this is a typical scenario to making aryl lithium compounds. Another application Another application for alkyl lithium compounds is, by deprotonation, is the preparation of enolates. Where you will have a hydrogen in alpha position to the carbonyl compound. And again, the pKa here is about 25. So this should be readily deprotonated by a compound like butyllithium, where butane, the corresponding alkane, has a pKa of roughly 50. And so butyllithium as a base should react this way easily. However, butyllithium is also a pretty good nucleophile. So the problems you are encountering here is that you might get the desired enolate formation. However, at the same time, it might give you the reaction as a nucleophile. Forming the addition product here. And so for this reason, usually you're not taking an organolithium compound like this for the enolate formation, but more commonly are lithium amides easily prepared. One very famous example is lithium diisopropylamide, LDA. Take butyllithium, diisopropylamine, and you're forming the corresponding lithium salt of the amine. And this here has a pKa of about 38, and still, therefore, absolutely sufficient to deprotonate just about any alpha hydrogen to a carbonyl compound. However, this is a so-called non-nucleophilic base. Because it is sterically so hindered that it will not react as a nucleophile. And there have been a couple of these which are being used This is another popular one. Which has the same idea, tetramethylpiperidine, the lithium base of this, commonly abbreviated as lithium TMP, or is there even a second P? TMPP piperidine? No, lithium TMP. This is okay. This has roughly the same pKs like LDA. That's something you would expect, of course. And then there is another amine base very often used. And this is lithium hexadimethylsilicate. Abbreviated as LHMDS. And this has a pKs of roughly 30, which is still generally sufficient to do deprotonations, to do enolizations. However, you can see that this is a somewhat milder base than you find with LDA and or lithium TMP. Does anyone have an idea why lithium hexylmethyl disilicate is a weaker base? And quite considerably. Think about these. These are 8 orders of magnitude. So that's roughly 10 to the, or not roughly, exactly 10 to the power of 8. So that's 100 million times. What's the reason for this? Any ideas? Something, I'm not sure if it's on the problem set or not, but we had last lecture, we were talking about stereoelectronic effects. And you might appreciate that silicon, being a third row element, has empty d orbitals. And so the negative charge from that nitrogen can be delocated into the d orbital. So you have a stereoelectronic effect again, why this is not readily possible or not possible at all with the corresponding alkyl groups. And again, you can see because of that hyperconjugation you have here, you see a significant change in acidity. So with this, only one more example or one more method for preparation. I would like to show you. And these are transmetallation reactions. So in general, again, the same idea like we have seen with the metal halogen or metal hydrogen exchange. You might also use a metal compound and an alkyl lithium compound, and then thereby you will be able to go from you will be exchanging the type of atoms, the metals on the alkyl residues. And again, usually it goes from what we had seen so far, it goes from more basic to less basic. And very often it is used in the way that you are basically more interested in preparing a certain organometal compound here rather than being interested in the organolithium compound. So let me give you a typical example. If you go from a L-magnesium compound and you're using triphenyl tin chloride, you will do the metal-metal exchange. You go from the more basic Grignard reagent here to a less basic, more covalent bound tin compound. So this is pretty much in line. However, interestingly enough, you can go now in with a more, again, basic lithium compound here, phenol-lithium. You're now even able to do a second transmetallation here, which will lead to L-lithium plus tetraphenyl tin. The reason that this works is that the tetraphenyl tin is precipitating out of the solution, and so therefore you're again driving the equilibrium to the desired L-lithium compound here. So this last method is not so commonly encountered for making organolithium compounds. It's more commonly encountered if you, for example, want to make tin compounds of this kind, starting from here a Grignard array. Nevertheless, there are cases where you can also use it ultimately to make the desired organolithium compounds again. Okay, with this, I would like to thank you for being here today. Wish you a good weekend. Problem set. First handout from the last lecture is already on the net. The second handout I will put on today. And then you have some problems you can solve for homework. And then I hope to see some of you on Monday in my tutorial and some of you in Michael's tutorial. Have a good weekend.